Right, I want to introduce the idea of capacitance. Capacitance is a coefficient that relates the charge on an object, a conducting object, to the potential of that conducting object. It turns out these two are linearly related. So in other words, if I have a conductor that has charge Q on it, the potential associated with that conductor, in other words, the potential the conductor has relative to infinity or to another conductor, so I'll write it as delta V, can be related to the charge through a simple linear coefficient. So you multiply C by delta V, you get the charge on the capacitor, okay, or the charge on the object. Okay, we're going to talk about this mostly for capacitors. Now it turns out this C, capacitance, will depend only on geometry of the object. Okay, so let me give a couple of examples. So the first simplest example is if I just have a sphere, a conducting sphere of radius A. Okay, and on that sphere I place charge Q. If I do that, then I know that the potential of the sphere, of the conducting sphere, is going to be Q over 4 pi epsilon naught A. Now, where did that come from? That comes from, I know that this sphere will produce an electric field that will go off, to infinity like a point charge. If I integrate, so that when you think about potential, it's the same as if I took a proton, a positive charge, from infinity and moved it all the way to the sphere. Okay, the work that's done will be this times the charge on that proton, but then to get the potential, I divide through by the charge, the test charge I'm imagining. So this is the potential of this sphere. Okay. Now you can see I have a linear relationship between the charge on the sphere and the potential relative to infinity. And that relationship can be rewritten, so I can write it as Q equals 4 pi epsilon naught A times the potential. And so this is the capacitance of a single lone conducting sphere. Okay. Okay, usually when we think about a capacitor setup, we don't think about a single conductor, although you can formally define, as I just did, the capacitance for a single conductor. Usually we worry about two conductors. Okay, and the idea is that we're going to have these two conductors in a circuit of some sort, connect them, and for example, we could connect them with a battery, and we'll talk more about batteries later. But what the battery can do is take charge from one of them and push it onto the other. So I can push charge plus Q onto this conductor, and because of that, I have charge minus Q exposed on this conductor, or you can vice versa, however you want to view it. Okay, so I use the battery to do that. Okay, and then the question is, by doing that, I've spent energy, I've separated charge. There's a certain energy stored in this situation, and I might want to release it to power something, to make my iPod run, for example. All right, but before we get to the energetics, let's talk about the capacitance of this object. So what you can show is that in this situation, the potential difference between these two objects, so delta V between these two objects, so the potential, if I integrate E dot dl between these two objects, is related to the charge. Okay, and so I'll find that Q will go like C delta V, where Q is the charge on this object, but it's also the charge on this object. Okay. And so let's consider a situation that we can calculate that's like this. And that's the situation where I have two parallel plates. So these are conducting plates. On one I put plus Q. On the other I have minus Q. And again, you can imagine these as part of a circuit. So I've pushed charge from one to the other. Now we'll assume they're effectively infinite, okay? And so the electric field in between these will be sigma over epsilon naught. We'll make this the x direction, x hat. And sigma here will be Q over A. So we can write the electric field strength is Q over A epsilon naught, okay? The potential difference between the plates, we're going to call this separation D. The potential difference between the plates is going to be negative integral E dot dx. Okay, and because the field is uniform, I'm going to get that the answer will be the following. Okay, and here I'm ignoring sign. So the statement of the capacitance is going to be a positive coefficient, and the charge, what I'll do is I'll use the charge on the positive object. And so this is really a statement relating magnitudes, the magnitude of the charge, okay, and the magnitude of the potential difference. So I'm not going to worry myself about signs at this point. And so I can rewrite this as Q equals epsilon naught A over D times delta V. Okay, and I've identified the capacitance of this arrangement. So the capacitance of this arrangement for a parallel plate capacitor, as we call it, is epsilon naught A over D. Okay, so this is the coefficient of proportionality between the potential difference between the two plates and the amount of charge that I put on the two plates, with the idea that I put plus Q on one, minus Q on the other. Okay, so this is the capacitance. All right, and so that's the capacitance for parallel plates. In class, I'll go over some other examples for capacitors, but let me stop here with this video.